So, as we move on today, we're going to start to take a look at correlation. Firstly, I just want to point out that up to now, you've only been considering single variable data. For all the statistical measures that we've looked at so far, the measures of location, from the mean to the median to the quartiles, we've only looked at single variable data. For the measures of spread, the interquartile range, standard deviation, variance, it's all been single variable data. And the diagrams that we've used so far all have referred to a single variable at a time. We now want to look at bivariate data. Now this is where data comes in pairs. If we wanted to investigate the height and weight, or the relationship between the height and weight of year 10 students, that would be bivariate data. Each person that we used in our sample would give us two pieces of data, one being their height and the other being their weight. Anytime data has two variables, we'll refer to that as bivariate data. Similarly, it might be that we want to compare science scores and math scores for year 11 students in the first round of mocks. One of the most useful things that we can do with bivariate data is to try and describe the relationship between them, if there is indeed a relationship. And we call that relationship correlation. Correlation can measure the strength and the type of relationship between the variables. The type of correlation is a qualitative assessment. We give it an adjective to describe what type of correlation we have. And there's three types. There's positive correlation, where one variable increases and the other variable increases also. Negative correlation, where as one variable increases, the other one decreases. Or no correlation, where there's no clear understanding of the relationship between them. We can qualify each of those and describe it with a little more detail. This is going to be the strength of the correlation. So both of these are weak correlation. Weak negative, weak positive. We determine or define the strength by how closely the data points fit a straight line. So the closer they fit a straight line, the stronger the correlation. So here we have some moderate negative correlation, and this is strong positive. It's almost forming a straight line. Strong negative as well, almost forming a straight line. If they did all lie exactly on a straight line, we would call that perfect correlation. We'll look more at that next year, but for now, we just need to be able to describe what type of correlation and the strength associated with it. So let's take a look at a few examples. Here we have students' English scores and their math scores and how they're correlated. I can see a positive correlation as the English score increased, the math score increased, but they don't quite follow a straight line. I would say this is weak positive correlation. Okay, the age of the people observed and the time that they spend on the internet each week. There's a negative correlation here, but once again, it doesn't quite follow a straight line. This is weak negative correlation. The distance traveled in kilometers and the cost of the train fare. Now this is definitely positive, but I can see that these very closely follow a straight line. They almost seem to be in order, apart from maybe 1 or 2 points. This is strong positive correlation. And here we have the number of people in a city called Dave and the crime rate. And as you can see that there's nothing that really connects these. There's no trend whatsoever. So this is no correlation. And of course, context can contribute to what you would expect to see in the correlation. And there's no reason why people being named Dave would have an effect on the crime in the city. Okay, whenever we're looking at two pieces of data, usually one of them would be independent while the second is dependent. And plotting these correctly is important. The independent variable, also known as the explanatory variable, would be on the horizontal axis, on the x-axis, while the The one that relies on the independent would go on the vertical axis. This is also referred to as the response variable. One variable explains why the other variable takes the value that it does. One variable is dependent on the second to have the value that it does. A simple example, the number of ice creams that an ice cream man can sell from his van and the temperature. Well, the number of ice creams sold depends on the temperature rather than the temperature depending on the number of ice creams sold. One of them initiates the other. One of them leads towards the other. Context is going to help you to set these out and just go through that thought in your head. Does this rely on the second variable? Does this variable rely on that variable? Now, there are two specific types of correlation questions you might be asked, and it's important you look out for the command words. So the word in the question that tells you exactly what to do. One type is state. State merely wants you to tell us the type of correlation. So positive, negative, no correlation. You could add in the intensity, the strength of the correlation at this point as well. So responses like weak positive, strong negative, moderate positive are going to be acceptable if you're asked to state the correlation. You will also be asked to interpret the correlation, and here you just need to include some context. So here we've gathered some data from a sample of people where they were asked their age and the weekly time they spent on the internet. We know we have negative correlation, and if we're going to describe the relationship between these two variables, we can say that as age increases, the weekly time on the internet tends to decrease. So just making sure you're referencing both of the variables and you're talking about the increase and decrease pairing between them. Now I want to point out that just because there's correlation does not instantly mean there's a causal relationship. A causal relationship means that one of the variables directly changes the other variable, directly causes the change in the other variable. If we have correlation, but we don't actually have the causation, we have what we call a spurious correlation. Let's have a look at a couple of examples. So in this scatter graph here, you can see that on the horizontal axis, we have the number of pirates, and on the vertical axis, we have global temperature. And if we didn't consider the context, we might make the spurious connection that the number of pirates in the sea directly affect global temperature. And I'm not sure we can rightfully blame pirates for increasing the world temperature. Here we have another example where a spurious connection could be made. According to the scatter graph, it looks like the number of fresh lemons imported to the US from Mexico is connected to the total US highway fatalities. It seems that as we increase the number of lemons imported, the number of fatal accidents on the highway reduces. Obviously, there's nothing connecting the number of lemons imported with the number of car crashes on the highway. You may well be asked to reference why a relationship is not causal, why the relationship between two variables that seem to present correlation are actually spurious and not causal. So this is you having a bit more insight to the data in front of you. Here's an example. Hideko was interested to see if there was a relationship between what people earn and the age that they left education or training. She says her data supports the conclusion that more education causes people to earn a lower hourly rate of pay. Give one reason why Hideko's conclusion might not be valid. In the scatter graph, we have the age that people have left education and the hourly pay that they get when they're 25 years old. Well, looking at the data, looking at the scatter graph, it does look that as the age increases, so the age that you leave education, your hourly pay is reducing. But that seems counterintuitive. The longer you stay in education, the higher your education, or the higher your employment prospects and the more money you'll get paid in your salary. But we just have to think a little bit deeper. Let's compare people who have left education at 15 versus 25. Somebody who left education at the age of 15 may well have had 3 or 4 jobs by now, and each time they're getting better pay from the job they moved to. Whereas somebody who stayed at university up until the age of 25 has potentially got a couple of degrees. Well, they're only going into their first job, and their first job isn't necessarily going to be the highest paying job they're going to achieve, but it is their first compared to somebody else's 4th or 5th. So that may well be the reason why people who've left education within the last year are not getting paid as highly as an hourly rate as people who left 10 years ago. So to sum that up, I'll just say that people who left education at 15 years old have been working for 10 years compared to people leaving education recently, so would have jobs that pay more. Okay, and we're just about finished, but before you move on to some practice questions, let's take a quick look at the specification and exactly what it is that students are expected to be able to show, exactly what the examiners are anticipating you will be confident on. While you read through that, I want to quickly remind you that it will be sensible for you to come back and watch this video at a later date, maybe come back in 2 or 3 weeks or before an assessment. And as you watch through the second time round, because you've done your practice, a lot of what you go through here should resonate with you much more. And you have a chance to really embed your understanding of the difficult concepts, the ones that have been flagged up as A star.